Hi again, and welcome to the second part of the introduction to the distributed systems part of the course. In this part, I'll talk a little bit about how to specify and prove secure distributed systems, and a bit about why we need to do that. And then there'll also be a little bit of vague advice, initial vague advice on how to design them. So let's get started. So you might earlier in your career have tried to kind of argue or prove that a program was doing the right thing. When I studied computer science here at this place, one of the things we did the first year was trying to argue that greatest common divisor algorithm was computing the right thing, using invariance. That's very fun. It's also relatively easy in that you have access to the entire program, which is very convenient if you want to prove that the program is doing the right thing. Imagine if you were given a program instead where I removed 1/3 of all the lines. So I just took a huge program with 300 lines and I removed the middle 300 lines and say, there's something here. I'll put anything here. Please prove that this program is doing the right thing. I mean, that would not be a fair task, right? The problem is that is the task we are facing when we want to argue that distributed systems are doing the right thing. So, I mean, in this course here, it's a course on distributed systems and cryptography, we're going to have, to a large extent, a focus on Byzantine attacks on the system. That means malicious attacks where we imagine that one of the servers have gone malicious and is behaving in a different way from what it was specified to do. So if we have 3 servers, 2 of them follow the program that we handed out, and the third one is behaving maliciously, doing anything. In fact, trying to optimize its attacks as to break the system. We are exactly facing a task where we want to prove that the system is doing the right thing, but 1/3 of the code is not only missing, it will be picked maliciously. And this can be extremely hard. I mean, how in a proof do we make sure that we kind of iterated or exhausted all possible attacks on the system? We're going to look a little bit of that. I mean, take a very brief look at that today and return to it in much more detail later. And a big success of cryptography and distributed systems is we have methods for doing that by now. But it's extremely slippery. In fact, it's sometimes even slippery to specify what a system is supposed to do when under attack. Because of course, I mean, if all servers are corrupted, the system cannot do anything reasonable. And there are some points in between where it might do some of what it's supposed to do, but not all of it. So even kind of specifying what do we expect from the system when under attack can be slippery. And because of this, there's a big and a strong focus in distributed systems on formally specifying what a system is supposed to do and formally proving that that it's doing what's supposed to do. Because it has turned out we cannot trust our intuition, neither in specifying nor improving these systems. It has to be done very rigorously, since security is very slippery. Okay? And what I'm going to do in the lecture today is take a first brief look at what's the general idea in kind of tackling this task. Okay. So remember this figure here. So we have this idea in distributed systems that we would like to develop well-defined middleware layers. For example, we discussed that something like a shared variable space as provided to us by Dropbox. We can look at that as a middleware layer with a well-defined API at all the clients. That's the left part here. So we think of the middleware layer as like one block here that just magically, if I put a file here, makes it appear over here later. Okay. So in principle, if I wanted to specify a box like that, I could really sit down and program it as one object, let's say in Java or in Go. I sit down and I write, my middleware layer should do this, and then I just give it this API. And I pretend that That's my specification of it. Okay? Knowing well that if I would actually implement this thing in practice, of course I would have different copies of some other code running on different machines, and they would have to coordinate via the internet. But there would be nothing preventing me from writing a single object here, let's say in Java, that behaves as I want the system to do. Okay, they just make an object with 3 interfaces, and they say this is how it should behave at machine 1, this is how it should behave at machine 2, and this is how it should behave at machine 3. And then I use a shared variable space inside the object to just program or specify how I want the system to behave. And then the programmer's job later be to take these 3 interfaces, put them on different machines, as is done here, and then use the internet to coordinate them as to make it behave as the way I specify. Yeah? That's a general kind of idea we'll take to specify systems. Okay? So abstracting that a little bit, we will later talk about what we call ideal systems and then network resources. Both of these being formal systems, something we write down. We can write down using math how we would like it to behave. But for now, think of it as just having been programmed in your favorite programming language like Java or Turing machines, something that we can give a formal semantics such that it actually means something. So not Java. The approach we would then take to defining security is to specify, as I said, this ideal system. So we write it down in some nice programming language with a formal semantics and say, this is how the ideal system behaves. If it gets this input on interface 2, then it will output this thing here on interface 3 and so on. Completely forgetting all the details about having to run on a network later. Just specify the ideal system. This system will be consistent and do the right thing by definition. Okay? So you will just write down how you would like it to behave. And that system that you write down, that is the specification now of the later real system. And then you also take your program, whatever system you have developed, and you write it down in the same formalism. So you write down what is the program running on all the different machines here. You also write down a model here of your network resource. So you model the internet in the same formalism. And then you show that this system here, what you would call the real system, which have a well-defined meaning now, behaves exactly the same as the ideal system. Okay? So that's the approach. This is a way to very strongly separate specification and implementation. Okay? So you specify what the system is supposed to do by abstracting away everything about the later implementation. Just really write down as concisely as you can the intended input-output behavior of the system. Then you later write down the big complicated program that you developed. And then you sit down and then you prove or somehow otherwise argue that the protocol is actually behaving according to specification. But the minimal thing you should have is a specification. Otherwise, you cannot talk about that the system is doing what you want it to do. Then we have this notion of securely implement. It's a term that's being used a lot, in particular in cryptographic protocol theory. And what's important about it is that you clearly see it's transitive. So you never talk about a system being secure. Doesn't make sense. You cannot take a protocol and say this protocol is secure, because there is no such thing as security without talking about what is it supposed to do. So you always talk about security as a relation between two things, the protocol and the specification. So you say a protocol securely implements the specification, okay? So just get used to that. Nothing is secure. Something can be secure relative to what you wanted it to do. And then, as I said, right, you first write down a specification in some kind of formalism. Let's write it in Java. How inputs and outputs should behave in the system. This is kind of similar to security policy. though also different. But I mean, the similarity is you try to specify what you want the system to do. And then you write down all the possible attacks, like really the bad stuff that could happen to the protocol. So if you wrote down your intended protocol and it has 3 parts in the protocol, you might model an attack by a Byzantine adversary by having the possible attacks being really that one part of the program is replaced by some other code that you don't know what is, that some adversary just plugged in there. The second you have a specification and kind of a list over the possible attacks you want to consider, you can then finally talk about the protocol implementing this thing. So we talk about the protocol implementing the specification under attacks from this set A of possible attacks. As I said, I mean when you sit and pick your attacks, your attack model, that again is very similar to what Ivan talked about in the IT security part of the introduction, namely threat models. You're picking what kind of threats you consider viable, or at least which ones you want to be secure, under which attacks you want to be secure. So the terminology here is a little bit different, but it's to some extent the same thing. There is one big difference though, namely when we talk in these terms of securely implementing, we have a very strong focus on intended behavior, and often we are talking about protocols and not physical systems. So we're looking at some formal specification of a protocol, and then what is our security policy here is a specification which is focusing on what the protocol should do. Okay, so this specification is typically when I get this input, I get this output. Whereas when you do a security policy, you are often focusing on the things that shouldn't happen. My machine should not get viruses. This part of the database should not leak to some outside person. And often here there is kind of a focus on the physical machines, the parameters. I don't want people from outside to see these things inside. Okay? So security policies are negatively phrased. It's about systems, physical systems. Whereas the securely implementing the specification is about abstract protocols and about, it's positively phrased. Under all possible attacks, the input-output behavior should be the same. That's why it makes sense to have different words for these things, and still keeping in mind that to some extent they are the same thing at different levels of specification. Okay. Also, when we talk about securely implementing, as you will see, often we will be much more formal than when you're specifying a security policy or a threat model. In security policies and threat models, often you allow yourself to specify what you want and what you don't want to happen in some kind of level of prose. I don't want viruses on my machine. When we're specifying securely implementing, we're writing down using math what the system should be doing. It should be these relations between input and output, and then you sit down and prove that those relations are there. And what we'll see is when we're specifying the ideal system and when we're specifying the protocols, we'll be using the same building blocks, something called interactive agents. So interactive agents are just machines, also called state machines, which is something that doesn't do anything in itself, but we look at it, we consider it a computer, and it's something that reacts to inputs and gives outputs. Okay? So it keeps a state, then it could get an input on a named port like A here, it could get 42 on port A, that will make it update its internal state, and then maybe produce an output over here on B. That's what's called an I/O automaton, something that produces outputs and state changes in response to inputs. We can write down the intended behavior of a system using an I/O automaton. An example of that you might have seen earlier in your life is Turing machines. They're example of I/O automatons. They get inputs, update their state, produce outputs. But there are many more kind of more pleasant formalisms for writing down I/O automatons. An object in Java is to some extent an I/O automaton, as long as you don't touch the disk or some kind of the operating system. So take your favorite formalism, and then you write down your ideal system as an I/O automaton with the intended input-output behavior. If the client on side A inputs this, then later on this part of the system, this output should be produced. You use the same formalism for writing down the protocol. So you take whatever protocol you have thought of, and you write it down probably as a bigger system of input-output automatons. One of them modeling the network, some of them modeling different parts in the protocol, maybe one of them even modeling the adversary. And then you try to argue that that ugly thing there behaves the same as that thing up there. Now, fortunately, that having been reduced to saying something like, these two systems on the same inputs on open ports, they produce the same outputs on open ports. So that's the kind of approach we will be taking in a later video. That's just to warn you what is up and coming. Another formalism for arguing about behavior of system is so-called trace properties, which we will also use quite a lot. So sometimes instead of taking a system and comparing it to an ideal system, we'll talk about what it's supposed to do by giving what's called trace properties. So the trace of a system, something like a protocol like up here, let me move myself around, have a protocol like this here, it has a protocol API up here. Its trace is just the list of inputs and later outputs. So whenever there is an input to the system, I write it down. And whenever it produces an output, I add it to this list of inputs and outputs. And that produces a list of inputs and outputs, and we call that a trace. And often we can use just trace properties to specify what a system is supposed to do. So by that I mean we simply write a predicate from traces into true and false, where true means we like the trace, false means this trace should never be produced. If I have a communication channel and it's supposed to be authenticated, for example, then we say that if I send 42, it should not deliver 43, or anything else than 42. That would be a trace property. That's a very popular way to specify what the system is supposed to do. When we do that, there's a very important distinction that we will return to several times in the course. So let me spend a little bit of time on that already today. Is this distinction between safety properties and liveness properties. Both of them are trace properties. It's something we would like the system to do or not to do. And the main distinction is safety focus on stuff we do not want the system to do, whereas liveness focus on stuff we would like the system to do eventually. And it turns out that it's very important to keep a distinction between these. So sometimes we also say safety properties are phrased in the sense that nothing bad happens. We're kind of listing all the stuff that shouldn't happen. Let's, for example, say we want to model an authenticated channel between a sender and a receiver. Then we say that if the sender sends M, then it does not happen that M prime different from M arrives, okay? My property on traces will be I'm looking on all inputs and outputs, and if all outputs match the same input, I'm happy. But if at some point there is an input and a different output, I output false and I say this trace we do not like. That's an example of a safety property. A very clean way to define what a safety property is to say it's something that is true for the empty trace. So when nothing happened, all safety properties are true. I mean, it's, for example, true in the beginning that it never happened that a message was sent and a different message delivered because no messages were sent. Right? So safety properties is something that's true at the beginning of time, and once they become false, they are false forever. Look at this example here. If it happens ever that a message was sent and a different message delivered, well, that is the case now until eternity. You cannot come back and delete the fact that a different message was sent. So that's an example of a safety property. Everything is good to begin with, and then when it's bad, you can never repair it. Liveness properties are kind of just the other way around. Liveness properties is something that is false to begin with, and once they become true, they're true forever. Liveness property could be something like if the sender sends a message, M, then M is delivered at some point, okay? At the point where the message is sent, this is not true, because, I mean, we didn't have time, the message couldn't travel to the receiver yet. So, of course, at the point where the message is sent, it's not true that it was delivered. This liveness property starts out being false, at least in this point here where the message was sent. And it could stay false for a long time, but at the point in time where the message gets delivered at the receiver side, the liveness property is now true. I mean, the message was delivered, and it will remain true forever. It will forever be the case that now this message was delivered. So that's an example of liveness property. We are often also throw in the extra condition that in any kind of point in time where liveness property is false, there should be a possible future in which it becomes true. This example here of starting from the point where message was sent, the liveness property that the message arrives can always, become true at some point, namely if the message arrives, right? So that's an example of a liveness property. Not everything is a safety property or liveness property. Some of them are mixes. If I say something like, whenever a message is sent, it is delivered exactly one time, that is neither a safety property nor a liveness property, because it can happen that the message gets delivered once. Now the statement is true, a message was sent, it was delivered once, but then it could later be delivered a second time, so now it becomes false again. So it's kind of a mix of the two. And there's a very important distinction here between safety and liveness, that you should be very careful about your safety properties. You should guard these with your life, and you're allowed to be a bit more relaxed about your liveness properties because you can always fix it later, right? Remember that a liveness property is something that can always later become true, okay? So it means if you're in a situation, say, where you have to choose between safety and liveness, let's say you know a message was sent, you're the receiver, and you're very anxious to receive the message. Now you have two options. You can either chill out and wait and see if the message actually arrives. So you can try to guess what the message is. Probably it's 42. You output that on your local API, and then you hope if the message ever arrives that it was 42. So we know intuitively which strategy is the right one, right? And that's waiting for the message. And the reason for that is if you try to guess the message and you guess wrong, then you broke a safety property. You did something you cannot repair. You gave 42 on your local API. Some program above you could now use that for doing something like pay out 42 money from an ATM, and later you realize you should just have paid out 2 money. That was bad. If you just wait for the message, then even if it was not sent and you deadlock forever, the worst thing that happened was you broke a liveness property. And you know what? Maybe the process in the other end comes up at some point in a month, sends you the message, you get it, and then you can pay out the money. So in this case, you did maybe something bad, you deadlocked, but you always leave out the possibility of repairing it later. So don't ever violate safety properties. If you have to choose, violate the liveness property. That's kind of the thinking in distributed systems. And that's why it's important to kind of write down the properties you want from your system as safety and liveness properties. So you just give the list of safety properties and the list of liveness properties. And we did see that some properties are neither safety property nor liveness properties, but you don't have an excuse because there's a theorem in distributed systems that we will not cover, which proves you that any property can be broken up as a disjunction between a liveness property and a safety property. And often, actually, it turns out they look natural. So, for example, the example that if a message is sent, it will eventually be delivered exactly once. You can write it as a disjunction of a liveness property and a safety property. The liveness property is if a message is sent, then it's eventually delivered at least once. That's a liveness property. Once it was delivered, it can never be broken again because we allow it to be delivered several times. And the safety property would be it never happens that a message is delivered more than once. That doesn't require that it ever gets delivered. It just says it's really bad if it gets delivered once. That's a safety property. If you take the conjunction of those two, you get the property when a message is sent, it's delivered exactly once. And they're both quite kind of natural. The good thing about separating them is you know which one you're allowed to break and which one you can be a little bit flexible. Okay. That was a long speech about trace properties, but they play a prominent role in distributed systems. Here's some advice that I have to emphasize, being a cryptographer myself. When you want to prove a system secure, or rather when you want to design it, that's probably where it happens, and you pick your attack model, the attack model under which you hope to design your system to be secure, you have to be tough on yourself, okay? It's very easy to kind of fool yourself for convenience and say, you know what, my computers don't crash. So I'm gonna program my system under the assumption that all machines just stay up forever. And messages don't get delayed, they just always deliver within a second. They don't get dropped. Not my messages, it's the message. I mean, all the other guys over there, they're using crappy machines and crappy messages, so their machines crash all the time. We know that, but not mine. I'm trying to joke here, right? But I mean, people do that, and they do it a lot. They just make it more subtle. I mean, it's very easy to fool yourself. You are the easiest to fool. However, don't do that. You have to be rough on yourself. So when you design a system and you're writing down what kind of attacks your system should be secure against, consider going through the following line of thoughts. So are you 100% sure that every machine in your system will never crash? No? Okay. Then you add crash faults. Remember we talked about crash faults in the previous lecture. So you really need to say, yeah, it's annoying, but my machines could crash. I have to be able to tolerate that. That means some machine that have a role in my protocol, it will stop doing it at some point. Okay, my machines can crash. Next question. When that machine crashes, are you sure that it might not accidentally send a weird message out? Like it's trying to send a message over TCP/IP. That's a stream of bytes. Couldn't it crash in the middle of that and deliver like a half message? Maybe when it crashes, it's because someone kicks out the power cable. And I mean, really, the operating system does some weird hiccup as the last thing. Yeah, probably it could. It would be weird if the machine just stops operating and exactly in between two messages in a well-defined way. Good. Now you have to add fail arbitrary faults that we talked about last time. That means the last thing a machine does before crashing is sending something weird out. That's really annoying because it means that every part in the system now have to be able to tolerate that. An otherwise honest part of the system might just send something wrong. That makes our life miserable, and we'll spend quite some time on that later. And you know what? You have a lot of machines in your system. Maybe when they crash, they don't really crash, but there's a bug in something. There was a bug in a compiler or the operating system. So the process really starts for a long time to send out weird stuff. Or maybe it gets hacked. Are you sure your machines will not get hacked? And one of the machines will really try to do something malicious over several days trying to break your system. No, you're not. Okay, so we add Byzantine errors. We're going to build a system with 10 servers. They're my servers. I mean, I'm doing the system. But I'm going to assume at some point one of them is going to be mad and just try to really destroy my system from within. Because if I don't, it will happen. And my system will be down. And my competitor over there, he will build a system that does tolerate it. So people would be using this system instead. So I'm out of business. So besides being a cryptographer and being mean to yourself when you pick your attack model, remember to also keep in mind when you specify what the system is supposed to do to break it into safety and liveness properties. And then let the liveness properties die first. Okay. That brings me to an important distinction in how we are treating time in distributed systems. Both when we design them and when we model a network, quite a lot of studies have gone into how to treat time and timeouts and clocks and so on, and we'll spend some time on that later. Now I'm going to discuss 4 prominent models here. So the easiest model to program and think about is the synchronous model. Here we assume that all machines are equipped with a clock. They might not be perfect, but they stay close to some time of nature. So, I mean, on the surface of the planet, we have a pretty good notion of global time in UTC. And we assume that all the machines have a clock and it's relatively close to this time. So they know within a few seconds what time it is. Furthermore, we assume that if 2 honest machines try to deliver a message between them, we have a known upper bound on how long that will take. It might be conservative, but we say, you know, if 2 machines are honest and connected and they really want to exchange a message, they can always do that within a minute. We just postulate some upper bound. And then we design our system under that behavior. That's the synchronous model. One big danger with the synchronous model is it allows to use timing to ensure safety properties. For example, if in a system with many servers, I have the safety property that if some process sends a message out, everyone should agree on what the process sent out, even if the process is corrupted and sends 42 over here and 43 over here. One way to assure that, a first step that doesn't work, but one way to assure that could be that whenever we receive a message from the receiver, we compare the messages. Now, of course, when we compare, one of the servers could be crashed. So I might not get a message to compare with. So I put a timeout and say, but I know messages arrive within a minute. So I just wait a minute. And if I don't get the message, I assume that the server is bad or crashed, so I don't have to agree with it. And then I proceed. But now if this one actually received 42 and sent 42, and I received 43 here, and the message was just slow to 2 minutes today, we actually saw different messages, but just didn't get time to compare them. So both of us progressed one output 43 to the API, one output 42. We violated a safety property because of a timing assumption failed. We don't like to do that because timing assumptions are fragile. I mean, internet connections do get crazy slow sometimes. Someone digs over a transatlantic cable or something, and the internet suddenly takes 10 minutes to deliver a message, or there is a massive power outtake that blacks out Latin America, and it suddenly takes 5 minutes to get a message from Alaska to South America. These things happened. And then it's annoying if there's an ATM in each end that starts just spitting out money. I mean, the same guy gets to empty his account in 2 different places and run away with the money. So it's a big fragile to base safety properties on timing assumptions. And that means the fully synchronous model, where we really fully believe in these timeouts, is more a theoretical construct in which we try to, in the first iteration, to design our protocols and to play with in a course like this. But in real life, you rarely imagine that you are really in a fully synchronous model. Timeouts sometimes just timing faults happen. So if you want to design a system that is really secure in the real world, then what do you want to, how do we then do it? And the first iteration is what's then called the fully asynchronous model. So what you say is, okay, so when I specify my system and when I design it, I'm not going to use time at all. In fact, I'm not even going to give my processes a notion of time. They don't have a clock. So when you write down the protocol, you're just not allowed to write .time anywhere, okay? Now at least you cannot get anything wrong with timeouts because you're not even using time. And also, if I don't have a clock, it doesn't really matter, but I'm also going to assume no kind of knowledge on message delays. They can be arbitrary. It can take a year. Sometimes we assume that messages eventually deliver, but that we don't know within what time. And that's the fully asynchronous model. This one is nasty to program. The first thing one will notice is it's impossible to distinguish between a slow server and a crashed server. I mean, if there is another server in the system and I didn't hear from it in a year, I don't have a clock, so I don't know even what a year is, but maybe if I'm running out of coffee, I realize a long time passed and I didn't hear from this server. I cannot, within this model, formally know whether it's crashed. The message just took a year. And that makes it very hard to achieve some quite obvious liveness properties. Like I would like in a system with 3 servers, where if I'm doing an election, right, I would like to get an input from all the other servers. But if there's 10 servers and 2 of them might be corrupted, I can ever only allow myself to wait for 8 messages. Because if I wait for 9 messages, it could be that the 2 out of 8 corrupted servers didn't send the messages. So I will only ever get 8. So if I try to wait for 9, I will wait forever. And I cannot make a timeout because I don't have a clock. That means also when our servers are honest, I will just wait for 8 messages and then progress. I just drop the inputs from 2 honest servers. You cannot collect a message from all honest and live servers and stuff like that. That's also annoying. So even though we protected ourselves by taking the clocks away, we did too much. But it is a model that we will actually look at. We can do some things in this model. And we look at it just to get used to asynchrony. Much more realistic model, which then try to put itself in between, is the so-called eventually synchronous model. So what it has in common with the fully synchronous model is we're going to assume that clocks are synchronized, that clocks are relatively close to physical time. And we will also assume an upper bound on message delivery. But we'll weaken the model a little bit and say, this might not always be the case. There will be periods in which the system is asynchronous, in which messages can get delayed arbitrarily long, and where clocks will drift. But we assume that always, again, at some point, the system will become synchronous for long enough. And then the way we try to design our system is as follows. During asynchronous periods where the system behaves weirdly and timeouts don't make sense, we make sure to never violate a safety property. Okay? So we never do something we cannot repair. And then we have to design our system so it's secure in that setting. And that puts on us, that forces us to design a system such that we don't base safety properties on timing assumptions, because then they would break during the asynchronous periods and the system will not be secure. However, what we are allowed to do is to ensure liveness properties using the timing assumption. So it could just be that the system is not doing anything reasonable when messages are not getting through, but in the periods where messages do get through, we should then be able to provide liveness. Okay? That's a very nice model that, it allows us to use time for liveness, but not for safety. And that's kind of the safe way to use time. A very related model to that is the partially synchronous model. That one instead says that there is a known upper bound on, now there's an unknown upper bound on message delivery. So it's guaranteed the messages that are sent will always get delivered within some time period, 10 minutes, 20 minutes, 2 days. But the idea is you as a protocol designer will not be told what the delay is. Another way to think about it is you first design your protocol. I'm only promising that there will be an upper bound on message delay. So you design your protocol and then I pick the delay afterwards. So if you build into your system that you think it's 10 minutes, then I make it 20 minutes and your system will break. So you're only allowed to use that messages will eventually get through, but without knowing when. That looks a little bit weird, but these models are very closely related. And if you can make a protocol that works in one model, it can also be made to work in the other one. Yeah. And we'll actually look at the partially synchronous model later when we look at blockchains. We'll take a very brief look at that thing. Then when designing a distributed system, there are some canonical tools or power tools that we try to solve. It's because time has shown us that if we can solve these tools here, then we can pretty much solve any other problem. And they're also didactically complete in that kind of the understanding we need to understand how to solve these things will allow us to think structured about many other problems, because these are also the hard ones to solve. One is leader election in a distributed system, where we have, like, let's say 100 machines geographically distributed, and we want to make one of them special. We want to pick a leader in the system. And this should happen. This should work even if some messages are slow, some of the machines are down, and blah, blah, blah. We should pick a leader which is alive. We should agree on who the leader is. Broadcast is the problem of sending the same message to all servers in the system. So we could have 100 servers, and there is one sender, and the sender should send a message to everybody. And we want to make sure that it's the same message we receive, even if the sender and maybe 10% of the other servers are corrupted, and try to make us not receive the same thing. That's complicated, and we'll take a look at that. But once solved, it's a very powerful tool to have in a distributed system. Very related, the problem of consensus. Here we look at a system where, let's say again, 100 servers, each of them have a 1-bit input, 0 or 1, angry or happy. And then they have to end up agreeing on the same bit. So that's not hard. They could just all output 0, but we also make this requirement that it should be a reasonable decision in that if they output a given bit, say 0, at least one honest, one correct server must have had that as input. Okay? So in particular, if all the servers are correct and all the servers have input 1, the servers cannot output 0. I mean, that's reasonable. That's a very powerful tool. Again, it turns out to check whether we all kind of at the same point in the protocol and so on. We'll also take a look at how to do that. And then there's the mutex system, which you should probably know, which you should know, which is about having some critical code. For example, the code accessing a printer or some physical device. We want only one process inside that code at the same time. Now, the complication being that these processes could be at different machines. So we could have a network printer and we only want one machine to access it at a time in a distributed system, so there might be 100 servers that would like to access it. Here are just 3 examples of how these tools can be used pretty much off the shelf to solve some interesting problems. One is, let's say, load balancing. If you have an email server for a huge organization like Aarhus University, in fact, often you have several of them. because they can't handle all the emails. Often because email servers also have to scan the emails for virus and stuff like that. So it is a computationally complicated task. And you would like to distribute it onto, let's say, 3 servers. And then what you have is you have a single gateway point. I mean, one server that gets all the emails in, and then it distributes them onto the servers behind. That also means if that one server crashes, the system is down. But then what you could do is have some of the workers elect between them the new leader and upgrade that. So if you can do distributed leader election, you can solve that problem directly. There's the problem of replicated state machines, which is taking a process, basically kind of a computer, and replicating it. So if you have some homepage for your business and you don't want it to be down, something like Amazon, where you have accounts, people can move money around, I mean, they can put money in, they can order goods and so on. You don't want that thing to be down. So you replicate it, it's running on several machines. But what you do want is, at the point where you replicate this process, you want it to stay the same on the machines it's running on. You don't want the account of a user to be one thing on one machine and something else on the other machine. So that's very complicated to solve in a system, say, where some of the servers might be Byzantine corrupted and actually try to destroy the system, and where some of the machines could be down, messages are slow, and so on. So if just given this problem here from scratch and trying to solve it, we would all fail. I mean, but there's actually a very simple way to solve it if we have what we call broadcast before. So the way it's solved in practice is you have all the machines start out with the service in the initial state. You just take some ground state. Everyone has 0 on their account. And then whenever an input arrives to the service here, you will just broadcast it. So you take this tool I talked about, broadcast, which can take a message and send it to all servers in the system and make sure that they all receive the same message, even if there's corrupted stuff going around. So you broadcast the input, and then all the machines will just run on that input. So they start from the same state, run on the same input, so they end up in the same state again. And that's what there is to it. You have to make sure that they receive concurrent messages in the same order and so on, and we'll take a look at that. But that's basically what there is to it. So copying a process and keeping it consistent, you can do that trivially if you can solve the broadcast problem. So we will look at broadcast in some detail. Now, having replicated your machine, it could happen that one of them crashes and then comes up again. And when it crashes and comes up again, maybe you want that it starts participating in the system again, gets up to date, such that you can later tolerate that another machine crashes and comes up again. Maybe over time you can tolerate that all the machine crashes and come up again, as long as not too many crashes at the same time. So one way to do that, and we touched briefly on that in the previous video, is that when now and then you write your current state to disk, and then when you come up again, I mean, you just run from that thing and then the inputs that was received since then. Maybe when you come up again, you want to make sure that you're in the right state. So what you could do when you come up again, you read the state from disk to make sure it's not corrupted. You send it out to everybody and ask them to tell you whether you're in the right state or not. Or rather, what you could do is send the state, have them compare it to their own state, and then you run this Byzantine agreement thing. You just vote on, do you all see the same state as I have? And if you massage that into the right thing, you can then make sure that everyone in the system will agree on whether this server here is now up and running again. And if it's not, you could buy a new server and put in, and if it is up and running, it's because someone actually said, yes, it has the correct state. At least one honest party voted yes, and therefore it is in the right state, and the system is consistent. So that's Byzantine agreement used as a tool. We'll also look at how to implement Byzantine agreement